All right, so that's mainly just to show you the variety that you can have, but now we're going to move on to the more traditional structure, which is a list. Now, these lists are very common in Prolog, and we're going to be using them a lot. We're going to be seeing them a lot as the course goes on. Now, we could define our own list in the same way we did for trees, but actually Prolog has its own built-in list structure and its own built-in notation, and it's actually got two different notations. One is the dot notation and the other is bracketed notation. So let's just have a little bit of a play with this. Now, yeah, the version, sorry, I was mentioning this at the beginning, that if you run this on the Mac, it's version 7. So if I type x equals dot of 3 comma 4, for example, it actually comes back with an error. So in order to get rid of that error, I have to say swipple minus minus traditional. That forces it to sort of run as if it was in version 5 instead of version 7. And then everything works fine. So you can get it to work, but you have to know, you have to be able to run the thing from the command line. Yeah, so you can either just type in the full path length, or you can add this to your path, or you can run it on the CSE machines. All right, so let's have a look at some of these examples. So if I say x equals dot 3 comma 4, this is actually adding, you have a list and it's adding a new element to the front of that list. So if I say dot 3 comma 4 5, it adds 3 to the front of this list that had 4 5. Now, well, so we often add things or take them off at the front of the list, and we often think of it like unrolling a carpet and just chopping off a piece of carpet or sewing on a new piece. Now, sorry that there's so much notation here, but yeah, I could nest this dot notation. I could say, well, I want to start with 5 and then add 4 to the front of it and then add 3 to the front of that. And I get back 3, 4, and 5. So this dot notation, if I write a really long list, this dot notation becomes quite cumbersome. So usually we prefer to work with this notation here, where we have a square bracket and then we put the things in commas. Now, there are some places where we want to make the head and tail of the list very explicit. So that's where we use this bar notation. So if I say, instead of the dot, I could say x equals 3 bar and then 4 comma 5. Well, make it a bit longer. 4, 5, 6, 7, 8. Then this list it's splitting the list up into a head and a tail. So the first element is called the head and the remaining list is called the tail. So now I can't, if I want to add multiple elements at the front, I have to do it like this. So this says take 5, 6, 7, 8 and add these two items at the beginning. So notice how these are just with a comma. So you've got to be a bit careful about the notation. So if I accidentally put these things in square brackets, what do you think will happen when I do this? A sublist within a list. That's right. So the head of the list will actually become this small list here. So you see, this is one item. This becomes one item, which is itself a list. So the first item in this list is another list that has these two items. And then this is the rest. So you've got to be a bit careful when you're programming that you say exactly what you mean. So it's always one item. Yes?
Can you have two identical elements within a list, or you can't?
You can have two identical elements within a list, yes, like 5, 6, 7, 5, 8. There's nothing. Oh. There's nothing wrong with that, yeah.
So how do you add, another problem is how do you add an element within the list, not just
How do you add an element within the list? Very good question. Well, you have to, normally we take elements off until we get to the point where we need to insert it, and then we add new ones back on. So we'll see in a minute how to do concatenating of two lists. Okay, now this head and tail notation can be used multiple ways around. So if I say x equals 3, 4, 5, and then I want to know, well, what's the head and tail of that list? It comes back and tells me what's the head and what's the tail. So this notation can be used to put lists together or break them up, right? Break them up. Okay, so what can we do with lists? Now, some of these things are actually built in, but it's often instructive to say, well, if a certain function wasn't built into Prolog, how would we write it? So here's an example here. I won't go through all of these in detail, but I'll go through some of them in detail. So there's a built-in predicate called member that tells you whether something is a member of a list. So if I ask whether 6 is a member of this list, it comes back and says true. If I ask whether 5 is a member of the list, it says true twice because it's a member twice, right? So that's actually built in. Now, if it wasn't built in, we could write it like this. We could say, well, if the first item in the list is x, then x is a member of that list. And then if the first item is not x, then we look at the tail of the list and we check whether x is a member of the tail. And so this would actually compute for us whether the thing is a member. Yeah.
Elements of lists are enumerated or no?
They don't have to be. So an element of list can be another list, or it can be an item. I can put Fred in here. Oops. And that's perfectly fine. So things in the list could be structured objects, in fact. Yeah.
Do they have index? Yeah, do they have index?
There is a predicate that will get out the nth element of a list. There is a way of extracting the nth item in a list if you want to do that. Yeah. Good. Okay, so that's all right. So member. Now, okay, so let's look at length. If we have a look at this list.pl, length is predefined, but I've written something called myLength. So it tells you that if a list is empty, then the length is 0. And if the list has a head and a tail, then I calculate the length of the tail, and I call that length of rest. And then I add 1 to it and call that length. So if I want to calculate my length of 1, 2, 3, 4, it comes back and says that the length is 4. And again, you understand what's going on by tracing. So it realizes that it has to apply this second rule. It says, okay, first is 1 and rest is 2, 3, 4. So I have to calculate length of 2, 3, 4. And then it applies this rule again and says I have to calculate the length of 3, 4, and then the length of 4, and then the length of empty, and then it comes back. So it's important to understand how these recursive calls work. So, I mean, there's a few different analogies that we can use, but let's say that it's a carpet. Someone gives me a carpet and asks me to calculate the length. So I don't unroll the whole carpet. I just unroll 1 meter, and I chop that off. And then I hand that to the next guy and ask, can you calculate the length of that carpet for me? And he takes the carpet, and he unrolls 1 meter, and he chops it off. And he's holding on to his meter, and he gives it to the next guy. And the next guy unrolls 1 meter and chops it off and gives it to the next guy. And the next guy's only got 1 meter of carpet, so he doesn't have anything to hand to the next guy. And then So that's what's happening in the top half. And then in the bottom half, the guy who had nothing says, well, you didn't give me anything for so the length is 0. And this guy says, okay, well, that was 0, but I've got 1 meter here, so that my length is 1. And he tells the next guy my length is 1. And the guy says, okay, you've got 1 and I've got a 1 here, so that's 2. He says, okay, my carpet had 2. And the next guy says, okay, well, you had 2, I've got an extra 1, so that's 3. And the next guy says, okay, you guys had 3, I got an extra 1, so that's 4. So that's the way the process works. Step by step, the carpet gets unrolled, and then it kind of gets, the answer comes back, and the information gets added together. Okay? Is there any questions about that? Yeah?
What's the name of the variable the same throughout the second?
Why is the name of the variables the same? Yeah, it's a different, okay, that's a good question. So each of these 4 guys is running the same code. He's using the same rule. But each one has a different value of the variables. So we sometimes call, this is sometimes called incantation, instantiation of the function, or I'm trying to think the word, is it incantation? Or there's some word that actually literally means summoning up evil spirits or something. I'm blanking on it. But you have the same code, but they got different values of the variable. For me, the length is 1. For this guy, the length is 2. Yeah, good question. But each guy's relying on the next guy. And in fact, almost all Prolog programs follow this kind of pattern, that there's a series of nested recursive calls until you get to a base case, and then you come back again. So everyone was using the recursive one, but the middle guy was using the base case. So if you leave out the base case, then the program won't run, or it'll come back as false, because the guy with the 0 won't know what to do with it. Yeah. Okay. Any questions about this? Yeah. And of course, there's some examples in the exercises. Okay, now we look at concatenating 2 lists. So this again is something that's built in, but we're pretending it's not existing and we're writing it ourselves. So we call it concat. Let's just see how this should work. So if I concat 1 and 2 with 3 and 4, it comes back with 1, 2, 3, 4. Right? So the idea is you have 2 lists of any length, and it should concatenate them together and make a big list. So how can we write a program to do this? Well, remember that it's easy to add things at the front. So this is the actual program here. So this is the base case, is concat. So if I'm adding an empty item to the front of a list, then I just get back the same list. Now, if the first list is not empty, then it must have a head and a tail. So what I do is I first concatenate the tail with the second list, and I get back this, and then I stick the item on the front, right? So again, I don't want to labor the carpet analogy too much, but you know, it's just I cut the front off, and then I ask. Yeah, there's the same issue with the carpets, except the guy at the end, instead of having nothing, he's got a separate carpet, and we want to sew the 2 carpets together. So he gives the second carpet, and then this guy sews his piece on, and then this guy sews his piece on, and this guy sews his piece on, and eventually you end up with a combined carpet. Yeah, and again, if we trace this through, you can try to see what's happening. So maybe it's better if we have a slightly bigger example. So let's say we take 1, 2, 3, and we concatenate it with 4, 5, and 6. So this is the whole trace. The first guy chops off the 1 and just has the 2, 3. The second guy chops off the 2 and has the 3. The third guy has something empty, so he just returns the second list. And the next guy adds 3 to the front of that list. The next guy adds 2, and the next guy adds 1, and this is what we end up with. Yeah. Now notice also the way information flows in a Prolog program. We're given these 2 lists, and these 2 are the inputs, and that's the outputs. Although this program maybe could be run the other way around. Let's say I wanted to ask what gets concatenated with 4, 5, 6 to give 2, 3, 4, 5, 6. It can figure it out the other way and say, okay, if I add 2, 3, and you can trace through that and see how this works. Yeah, so the information can go both ways. Okay, so this example is, there's this cost example. A slightly simpler version of this is just adding up the items in a list. This program adds up the items in a list but is incomplete. So this says, okay, if I give you a list consisting of a head and a tail, what I should do is add up the items in the tail to give me tail sum, and then add the head to that, and it gets me the sum. Okay, so this is logical, but what's missing from this program? The base case, right? So what do I need to add to this to make it work? What's going to be the base case? Sum of what is what? Sum of an empty list is 0. That's right. So again, you can trace through this program. Let's say I want to sum 1, 2, 3, 5, 6. What's the answer? And again, it kind of strips items off the list one by one until it's empty, and then adds them back one by one. 5 plus 6 is 11, 3 plus 11 is 14, and 2 plus 14 is 16, and 1 plus 16 is 17. Yeah. So it's the same kind of story with all of these programs, and you can have a look at this cost function. This cost function is slightly more involved. The list here consists of either cornflakes or chocolate or crisps, and then a price is specified for each item. So this program, instead of just adding up the item, it uses the item to find the item cost, and then it adds the item cost to the total cost. So you can trace through this in your own time. Well, here's a trace of it here. Okay, so are there any So we've seen a few things. So we've seen manipulating and concatenating lists, finding the length of a list, and adding the items in a list. Are there any questions at this stage? Yeah.
If the list is too long, is that possible to stack overflow?
So the question was, if the list is too long, is it possible the stack will overflow? I'm glad you asked that question. So for these programs, the execution time is just proportional to the length of the list. So you won't have any problem. But the next example we're going to look at is removing duplicates in a list. And I'll show you that if you write the commands in the wrong order, the program, it actually won't run out of memory, but it'll just take an exponentially long time to run. Next week we'll be looking at search techniques, and we'll see examples where programs actually run out of memory. Yeah, you get a stack overflow. Yeah, that can happen. If the list gets too long, you will run out of memory, but you need to write a program that will actually build bigger and bigger lists, bigger than your input. Yeah. Okay, good question.